So what we today you will have a fairly heavy dose of subject, because I want to complete this basics of DSP, and also I will not include this in tomorrow's exam. So that's if at all there is any relief. But and second thing is for tomorrow's exam, of course it will be, you don't really have to refer to any book or something if you followed what is going on in the class, but it won't be, I can't say what it is, whether it's simple or complex kind of a thing, but whatever is done in the class, your understanding is what I am going to test. Okay. So, all right, let us continue with this the properties of DFT. Just want to spend 5 minutes on this and then move on to the next topic. So you recall that yesterday we were discussing this. One is, of course, I didn't mention it, but you can also see what is called the symmetry of real and imaginary parts. I think it's very easy to understand. That means if xn is real, this is only if xn is real. If xn is real, you will notice that the real and imaginary parts of xk will have some symmetry properties. The real part will be even symmetric and imaginary part is odd symmetric. Okay. And anyway, that I am not going to prove, but it's very easy to verify this. Just write down those equations and observe real and imaginary part, sine and cosine part of it, then you will know. And we also mentioned what is called the, of course, conjugate. And only thing you have to worry about here, maybe I should have written that property a little later, but anyway, the conjugate symmetry. Okay. Periodicity. Actually, this is the one that led to FFT algorithm. You asked me if you don't understand. We discussed this yesterday. This I mentioned and I just left it. This should have come after something, but anyway. We also mentioned some, what is called the time and frequency circle representation. We discussed this also. The key thing here, that's why I keep saying that this should have come probably A, B, C. This should have been C. The only reason for that is you would see that the symmetry properties, you have to see it in relation to a circular behavior, because otherwise we say, okay, if there is a function with a time t is equal to 0, let's say, then symmetry means you look at on the positive side and negative side. Even symmetry means it's just a mirror image. Odd symmetry means mirror image and then flip down. All of you know what is meant by it. So that is what you will see in a normal symmetry properties. But unfortunately, this is a circular, this one. So in relation to circular representation, you will have to see the symmetry properties. So you have to get used to this a little bit. In fact, for entire MATLAB displays are based on this. You see, in fact, if you don't understand this, you can't understand anything that is done by MATLAB. Of course, you may still do something, but get some wrong results, which is what is happening again, as I noticed with many people. But you must understand this, and this also that means the interpretation. Why is it all coming? Because sampling and blocking. Sampling and blocking is the one that forced us into the circular property. Once you sample and block it, you notice that you are only seeing the periodic sequence of that in our DFT relations, and that's exactly what happens. And this is necessitated by the fact that you want to perform these operations in a digital machine. All of you get this point? We have So, this is very important to understand. And so, now when you talk about a symmetry, let us say in time circle also you can have symmetry. In fact, many of the although in the current situation we are not doing it, let us say x and n is equal to 0 to n minus 1, it need not have symmetry x n. But even if it does not have a symmetry, you notice that x k will have a symmetry. X k will have a symmetry with respect to this line. That means all the values on top will be just conjugate symmetric of the values on the bottom. This value will be just conjugate symmetric. What do you mean by conjugate symmetric? Real part is same and the imaginary part is complex conjugate. That you understand what I am saying? That means complex number will be a complex conjugate. You understand? So, real part will be even symmetric, imaginary part will be odd symmetric. And this is very important, otherwise all your interpretations will be wrong. And all of you get the idea here? So, the symmetry property is with respect to this. That is why in manipulating that, and also you notice if it is symmetry, after all if I know the top half, I know the bottom half, correct? If I know the top half, I know the bottom half number of points, but I started with n points here. What happened? Why is it that the n by 2 points are enough? Very simple question. I thought the answer will be instantaneous, immediate, but it does not seem to happen. Huh? Yes. So, even though you have n by 2 points here, it is n by 2 into 2, the real and imaginary part. So, you still have n numbers, unknown numbers. You understand what I am saying? Although you have n by 2 points only here, because the other two n by 2 points can be reconstructed for real data, you notice that my xn and xk, they can be interchanged. That means from xk I can get the xn, vice versa. Excuse me. So, these n by 2 points should be enough for me to reconstruct, but where are these n by 2 are complex numbers. So, that means they are equal to real numbers, to n real numbers. So, that is how you do not lose any information, these n information is available in n other real numbers. So, and it so happened that you organize them in a complex numbers. All of you get the point I am saying? So, suddenly you do not think that somewhere something is lost, nothing is lost here. And because of the symmetry and other, in fact, lot of FFT algorithms are exploited by doing in a slightly different way. Even if you are given a sequence, you create a symmetric sequence out of this and then do all of this. That also lot of people do. Number of studies are made. Let us not worry about all of that. I am just saying that you can do lot of manipulations here. It depends on how you want to look at. There are many practical situations where you would like to look at some intermediate stages in a particular way. That is how the data will be. It is only for convenience. Otherwise, it does not have anything to do with the logic or with the computation. So, this interpretation of the symmetry properties of real imaginary parts is important, and I would like you to try this thing on the MATLAB. You see, you compute the MATLAB, and then that is why if you say FFT, suddenly you get all the complex values, even if you had given a real as input. And look at those complex numbers, and typically if I am not right, if I am not wrong, if it may not display all the n values, it will only give half of them, because the other half can be reconstructed, but sometimes it will give full also. I do not remember how the FFT or what output it gives, but you can check all of this in the MATLAB, there is no problem. I want you to understand that. And then we have the important things like I said appending with zeros. Notice that if it is real like this, then I could have appended zeros here and I had no problem. And appending zeros, notice also this helps you to, and whereas appending zeros here will be a problem. Not problem, you have to keep track of the fact that it is symmetry properties are preserved. So, in order to preserve symmetry property, you start appending zeros here symmetrically. That is all you have to do. And notice that they are all complex zeros. That means 0 plus j0. That is what you have. So, append that. What is the, why do you need to do that? you want to do that if you want to resample the input. If you want to resample the input, you understand what I am saying? That means instead of let us say I had n samples, I wanted n plus m extra samples here. How do I do that? That means same interval I want total number of samples, not n plus m. So my values will not be exactly at the same instance now. Now it will be 2 pi by n plus m. Or my time interval gets compressed. If it were earlier t, now the new time interval is n by n plus mt. You understand? So I have to create that new sample here. How do you? It's very easy. That is the advantage. That is very easy because all that you have to do is append m zeros here, but making sure that it's symmetric here. Take the IFFT of that by using m plus n DFT, then you will get this. Very simple. Okay. Just somehow try to play with these things very easy, and without this kind of a simple understanding or simple manipulation, even if you cannot use any of the tools that are provided, especially in MATLAB or any signal processing tools for that matter. Okay. So, and this is of course, as I told you, this is unfortunately this is the price you have to pay for if you want to use this digital system. That means for blocking, sampling and blocking, you have necessarily ended up in a circular representation, whether you like it or not. Why? Because after blocking, you don't want to see, there is nothing like rest of them are 0. As I told you, every time you define something, you have to define from minus infinity to plus infinity as far as signal is concerned. So in this case, what you are doing is, you are defining as though the same number of samples are repeating. And the best way to show that it is repeating is arrange them in a circle. You see, it's very important. Just because you don't see doesn't mean that it vanishes somewhere. In a computation, you have to necessarily take into account. So that is how this periodicity is forced upon us by the for the convenience that you are going to have of a digital manipulation. You get the point? And accordingly, the interpretation of many things are important, and also there is a possibility of going back. In fact, whole DSP is for this purpose only. It is only to understand this, what kind of a manipulations you do and how to interpret the results. If you don't, imagine from input to output, if there are dozens of transforms that takes place at various stages, finally you get what you get is garbage. That's all. You don't even, if you don't take care of the intermediate. In fact, this is typically the problem with many students, and not only students, even researchers, if they don't pay attention to this part of it. Okay. Anyway, I think that is appending with zeros results in what, as I told you, is called. Anyway, while plotting this, of course, typically what you do is you plot 0 to 2 pi, and then of course, in fact, you don't even plot to 0 to 2 pi, to 0 to pi you will plot, and those number of points. So typically xk, you plot, let us say, magnitude of sk, you plot something like this, and then of course, this also becomes symmetric. That means if you had some shape here, you should have some shape here. You get the point? So you always refer to that circle. So it's only that many points are there, n0 to n minus 1, 0 to n minus 1 points are there, and notice that in this circle 0 and n by 2, 0 and n by 2 are common points. Even if you mirror image it, what happens? Flip it around the axis, 0 and n by 2 will be same. So you must be take care of many of these things, and you, so it is not that you can take a mirror image, it's all periodic sequence, you are just collecting on period. So these are very important things that we need to understand, and typically for a real data xn, this is symmetric, so normally this is not even plotted. Okay. So these are the things that you should understand. So appending with zeros, as I told you, performs what is called the spectral interpolation, and you can do a similar thing of course in the other domain. And then I say inserting zeros. Inserting zeros, that means again I can first let us say I have xn and with some number of values here. So So, what I do is I insert m zeros and create a new yn, let us say. All right. So, same samples that I have and I insert zeros here. This is my new block. Okay. That is how you do, and you can visualize, since this has to periodic. So, you can see on the time circle how it goes, that we have already discussed. So, this is sorry, I am sorry, it is not appending zeros. This is now I want to insert zeros. Let me, this is appending zeros. Now I want to insert zeros. Let us say if my original xn is same, I want to insert zeros here. Notice that first of all, when you say the sample is 0, 1, 2, 3 sample index, there is nothing like half and 2/3 and so on, there is no such thing. So, when you say you are inserting, you have to necessarily stretch it to say n. Obviously, inserting system uniformly, if you are to do, if you want to insert 1 0, let us say in between these two, the number of samples have not necessarily have to be 2n. So, the last sample will be 2n minus 1. So, like that, if you, let us say, just for the sake of argument, so I insert 2 zeros here. So, if I do that, then I will have the total number as, last sample will be 3, where the non-zero samples will be exactly same as the first n samples. You understand what I am saying? So, anyway, I am not going to write the equations for that, it is very easy. So, now I have a block of 3n minus 1 samples. So, if I perform the DFT on this, how do I perform the DFT on this? Simply write xk on this new data, call this as yn. On this new data, yn e to the power of minus j 2 pi by 3n into nk. N is equal to 0 to 3n minus. And what will be k? K is equal to 0 to 3n minus 1. Now, the question is, as you already noticed that we have not added any new information, just everything that we have had. So, what is the effect of this? This is what I was, so if I plot this, let us say on a linear scale, notice my 0 to 2 and everything is 0 to 2 pi, and that becomes, if it is n, there will be n numbers there, if it is 3n, there will be 3n numbers there. So, let us assume in the first case, my xk will be some shape like this, just I am not going to write the samples here, just let us say these are the samples, xk correspond to xn. Okay. If this is what you have, notice that there are n samples here, okay, and 0 to n. Now, what you do is, if you have same 2 pi, so you notice that you do not really, the actual axis is not changed, but the number of points have changed. Number of points have changed to 3n. So, it will be 3n minus 1, and of course, there will be again some pi corresponding to 3n by 2. Now, what will it look like? Obviously, you see that is what we are after. It is very, very simple. I am not going to write the equation. In fact, from that everything is evident, but anyway, I skipped that part of it. You just have to plot this. So, this will be like this. Okay. me worry about the axis later. I am not able to adjust to this axis. All I want you to understand here is, whatever I had in this n by 2 samples, okay, they just get repeated like this, and likewise symmetry, this gets repeated. Okay. So, that is what you understand what I am saying. So, you will have anyway, don't ask me to plot this, you see. So, the point, it is best thing is to get it on the MATLAB, you will get this. So, basically what it means is, the spectral shape, now there are 3 endpoints, notice in the same 2 pi. So, this original shape just simply gets repeated, because you are not added any new information, but be careful that since your range is only 0 to 2 pi, if you blindly take this, this will be your as a new spectrum, then you notice that this will be, instead of 1 strong peak there, now you had 3 strong peaks kind of a thing. That is what you tend to interpret. You get the point I am saying? But you should note that you have got this by inserting those zeros. You get the idea? So, it is I mean, it is actually this insertion of zeros should be discussed in about 1 or 2 classes, because some equation, simple things can be written, but I want to skip that because I want to go to more important things. These are all, this is what you want to study in DSP. So, the third one is what is called the deleting samples. Notice that I did not insert anything, I inserted zeros. You must understand that. Now, deleting samples, what is meant by deleting samples? Suppose I had n samples here, deleting means every alternate one you take, let us say, then n samples become n by 2. So, if it is n by 2, my 2 pi by 2 pi, here I had n samples. So, now in 2 pi I will have only n by 2 samples. So, what are those new samples that you get? It is very easy. All that you have to do is simply take this and push this whole thing like this. Let us say, if I like this, and this whole thing comes like this, you see. So, now this 0 to pi becomes 0 to 2 pi, and the new values will be sum of these two. So, that is the aliasing. As I told you, you take that circle and curl it around once more, you see. So, the resulting values that you get, you simply sum them up. So, that is how the so obviously you will not get that shape anymore. So, notice in the first case, in this case inserting, you have all the information that you want. So, you do not lose anything, but here you lose information because you have taken every alternate sample. So, these are the important 3 important operations. Of course, there are many more, but these are the 3 important operations. It will be good to understand. Of course, depending on your time that you have at your, of course, you will have time. What is there? You spend some time in the lab, or if you have MATLAB in your computer, just experiment with this. No amount of explanation in the class will help. I can write a few equations, there is no problem at all, but that also does not help. In fact, that confuses you only. The best thing is to get a visually what is the feel for this, and you can't ignore this, unfortunately. You can't ignore this, because I think you already did one experiment, effects of DSP. So, when you downsampled it, you listen to speech. You see, so that speech is not same as the original speech. So, what is the loss? What is it that you have lost? So, these are the things that you would understand, and it is much more effective. Those who cannot appreciate the changes in audio, but at least you can see changes in video or images. So, it can be seen much more effectively in images for that matter. You see? So, it is all that means you can insert zeros or remove some pixels or insert some pixels, you can see the resulting image that you get. You get the point I am saying? So, these are all something which you have to play with, and there is no amount of explanation here, and you know, they do not take whatever I have written as the exact one. You have to go and look at it on the screen. and then you will get to see the effects of this. All right. So, this is and the last part here before we close the discussion on this DFT, very important, but unfortunately I do not have time to do this, but we have to we use it so extensively in our for manipulating the speech signals. EFG is what is called convolution, and that is circular convolution. Circular convolution. See, we know what is convolution of two sequences. If you have, let us say, x n and h n, convolution of these two, you recall we did x k, h n minus k, summed over all k. That is what we said. That is all nice to say when you had infinite sequence and so on and so forth, because I can flip it, shift it, sum it, and all this I can do. But the moment they are in circular, you are in trouble. You see, first of all, you can see that flipping equivalent, you have only one circle here. So, the flipping equivalent is much harder to visualize here. You get the point I am saying? And of course, whether it is harder or not, you have to do it. But in this case, what happens is, if you have points and a circle, flipping simply means that just take a flap up, that is, take this on top and that on bottom, then it is almost, it is equal to flipping. You see? So, now imagine there are two sequences. Of course, if it is, let us, obviously you have to deal with a block of data, you can't do infinite summation there. So, the moment you have a block of data, see, this is one, even yesterday I was talking to some of my research scholars, and the mistake they are doing, but there is nothing I can do. You see, I can only explain the class, tell a few times, but they keep on doing these mistakes. But you have to learn yourself. There is no amount of explanation will help, but that's the result that you get are first or two or three or first few attempts, all the results that you get are wrong. There is no question about it. No matter how good you are and how careful you are, but slowly you get to learn how to do this. Now you can see the effect of that here. You see, I will take xn is a one block of sequence arranged on this circle, time. This also time circle, this also time circle. My hn, exactly same number, let us say n samples I have, and arrange them on this block. Now I want to convolve these two sequences. If it is a normal linear convolution, I have xn here, a block of samples, something like this, and a hn here, and a block of samples. Of course, when I say this, these are samples of this. So, I know how to do that. What do? Take it, flip it, and then multiply these two, and of course, while doing that, I assume that rest of the values are 0. That is what I do, and sum them. That is what I do. And in a circular one, I can't do, because rest of the values are not 0. Because the rest of the values are not 0, now you see what happens. You have to understand this carefully. You remember what my samples are? The samples are located on the two n equally spaced points on this. So, these are my x samples, likewise these are my x samples. So, imagine one circle here with those sticks on the x circle, and another circle with y circle. So, you have one circle here, another circle here. Arrange the circles one below the other just as you arrange them. Now, what to do is take the second circle data, flip them. Flip them is like my h minus n. So, what is meant by flipping? Of course, you can do one thing, there are several ways of flipping it, but one way is just do this, because this 0th one should go to this one. I suppose you know what. So, after doing that, h minus n, the equivalent is flipping. Now, what is it that you do in the linear convolution? After flipping, you first take the product of these two to get the first value, product of these two, and then sum it to get the first value. Then what do you do in linear convolution? You shift it to the right and again take the product, you get the first value like this, and shift it to the left again. You have to do it with the shifting infinite times to get all the data. Now, in the circular one, what happens? You multiply. So, after doing this flipping, take the product of these two. You see, for the same finite data, when I flip this, and then take the product, only these samples are multiplied. But in a circular case, you notice that I flipped it and take the product of these two, all samples are involved here. So, the first sample I am getting is wrong already. The first sample I am getting is already wrong, because you see, when I flip this, what happened is, it is not that one below the other, because the other got distributed in the same unit circle. So, after flipping, that means like this and then multiplying, you see there are n multiplications here, n summations here, all of them are non-zero, multiplication plus summation. So, it is not like in this case you have h minus n kind of a thing, you multiply these two and then keep shifting. You are not lucky to do that, even h. So, the resulting y0, if you want to call it, itself is wrong here. You get the point? And now what is the next value? How do you get it? So, you have, after flipping, that means you h minus n you got. Shifting means simply means rotating the circle. Rotating the circle by 1 unit. That means what was earlier 1 becomes 2 and like this. So, rotate it, keeping the first one fixed, and now again do n multiplications and summation to get the second value, third value, fourth value. Like this you have to keep rotating the second one until you finish one circle. So, finally, you will get how many? N numbers. You get the point? You get n numbers, and if you continue to rotate, you will get the same numbers again. There is nothing you can do. You see? That is called a circular convolution. But this is called a linear convolution. In the linear convolution, if I had n numbers here and n numbers here, if I flipped it and did this on both sides, what is the total number of non-zero values you will get? 2n minus 1. 2n minus 1 non-zero values that you will get. So, that means the result is 2n minus 1, although you have taken n and n. Get the point? So, but in my circular convolution, the result I can store only in n. So, I did not provide enough space for it to store the result. That is why that error is coming. You got the point I am saying? So, the only way to avoid that is, you still want to, you may see why I should go about this headache, why can't I do this? I will tell you why you should do that, why you need circular conversion, but before that let us see how to avoid this. Very simple. All that you have to do is, the time circle n samples only are given, but make them as 2n minus 1 samples right in the beginning by appending with n minus 1 zeros here. Append this with n minus 1 zeros to create 2n minus 1 samples. Append this with 2n minus 1 zeros to get the 2n minus 1. Now, you flip this. You flip this, notice that the 0 values would come there. You get the point I am saying? So, when you have all the zeros non-zero samples and then you inserted zeros. Now, you by doing that flipping, you will see that the 0 values will come there. Now, you multiply, you will get exactly the correct result as you get in a linear convolution with these two n. Got it? So, anyway, this is called a circular convolution, and it is why do you need a circular? That before that again, I just want to generalize this. I said n and n. Why should I need n? I can have xn n non-zero samples, hn m non-zero samples. That is possible. And if that is the case, the number of zeros that you have to append with for xn will be m minus 1 and for hn will be n minus 1. So, that the total will be n plus m minus 1. That is the minimum. If you want, you can append more zeros, but the minimum that you need to append to avoid the effects of the circular convolution is this. Now, why all this circular? Why can't I write a program to do this? Circular convolution is extremely useful in computation. Why? Why? You can see already, if you have two sequences convolved like this, that is what you want to compute. And we also know this is same as the Fourier transform of scale factor I ignore. So, Fourier transform of convolution is a product of Fourier transforms. So, now you notice what I can do, and I have a very efficient way of computing the Fourier transform. I should have written xk, anyway you understand what I am saying. So, I have an efficient way of computing, that means from n squared I can get n log n. So, that advantage I want to cache on it. If I want to compute this, even if I am appending it, it does not matter. Compute the Fourier transform of this, compute the Fourier transform of this, take the product of these two Fourier transforms and take the inverse of that, you will get the convolution. So, by applying 3 Fourier transforms of an extended this one, you may say all this overhead might cost you. No, if n is of the order of 1000 or 10,000, you can see that the computational saving is still significant compared to the linear. You can calculate and see linear convolution for each computation of the output sample. You need some n plus some whatever it is, some number n plus m minus 1. So, that many n plus m minus 1 squared computations you have to have there, whereas here it is simply some 3 times or 4 times that log. So, that is the advantage. And you can see, you may say anything, but no matter how much computing power now we have, but I am talking about 30 years ago when computing power was very expensive. So, this is a very effective way of computing. And of course, even today it is, because what happened was earlier in those days they were looking at only smaller blocks of data. Now you are using larger blocks because you have more computing power. Okay, that is the advantage. This is called a circular convolution, and its use is because its application is because it is an efficient way of computing this. But the disadvantage is, of course, you have to worry about this errors that you get unless you take care of appropriately appending it. It is exactly same as that. Yes. You can try that. It is very easy. All that I have done, in fact, any amount in my classroom lecture will not help. You have to go back and then visualize. That is why I said once you append it, you flip it, your Hm minus n will come. You can see all these values will be 0. Now you multiply them, it is exactly same as that computation. Only the first sample there is a common thing initially, and then slowly just, okay. So you try that, it will all come out all right. So there is no problem, because you can see n minus m, one sample 0, there is m minus 1. So when you flip it, you can see that the other part is all zeros. Just to visualize and write it on paper, it will be very clear. And of course, if you, that is why you always, that is the minimum that you have to add. If you still do not know how to calculate, add some more zeros, it does not matter, nothing lost. Because after some circle rotation, one full, the only zeros get multiplied with this. So there is no, you will get only 0. What happens in a, it is exactly same. It is exactly same. You do circular convolution Fourier domain also, but only thing every time you have to worry about is that complex number, that symmetry properties, that is all. These are all very, because you do lot of convolutions in the convolution operations in the Fourier domain, just as you do it in the timeline. It is a, you see, I know, I can see the difficulty of students, but even if you had gone through this for a semester course, at the end of it you will be in exactly the same position of those who had gone through only 1 hour course in this. Why? Because it requires that practice, that intuition, that effort to understand. Most people do not try to make that effort. You simply blindly copy some examples, equations and so on. No, any number of examples is useless unless you get the real picture in your mind. And you could make up your own example. Do not worry about examples that most of the time what happens, why you can't understand or you appreciate much worked out example is because every step looks nice, but you lost the overall picture of what it is. On the other hand, if you make an example, then you know what you are doing. You can't move to the next step unless you know what you are trying to do. And if you do that for a simple cases, it is very, you do not have to do 512 points or 1000 points, just do it for 3-4 points, that is enough. You will get a full picture of this, and there is no amount of lecturing or explanation will help you to convince on this, but this is you have to practice it. And along with this, there is another thing which is very easy, but which you in speech we use both of these, circular correlation. Instead of circular convolution, you also use circular correlation, and which we use, as you will see in the rest of the course in speech. So it is very easy. All that, in fact, it is much easier than the convolution, but operations are exactly same. correlation of two sequences simply means, suppose I have two sequences, it is correlation, convolution symbol is this, correlation is given by deceptively, it looks like it is exactly same as that, but they are very different. They are very different, that is h n minus k and this is h n plus k. And what is it equivalent to? In this case, let us see first in the linear case, linear convolution case, all that you are doing in a convolution is do not flip it, that is all, rest of it is same. Take these two as it is, multiply them and sum them, you will get the first value. And now you shift it to the right by one sample and multiply, sum, you will get second value, third value, and now shift it to the left by one sample and then product and then sum, you will get another. Keep shifting to the left and right to get the correlation. So, that is all the difference. So, in this case, arrange them in samples, now you do not flip it, but just simply rotate it. Rotate it, you will get the correlation. But of course, again same problem as in a convolution, if you allow, just as if you have n samples of xn and m samples of hn, then the total correlation values will be n plus n minus 1. So, you must append this along accordingly with zeros in order to perform, and this is the one you already used it in MATLAB in our speech in the experiments, and you will use it more often later, and you should understand that first of all how to compute it. So, that in fact, it is how it is implemented in the machine is not by standard operation, but the DFT. MATLAB code uses the DFTs to compute the circular convolution, otherwise convolution is a very time consuming operation, especially the block is very long. You get the point I am saying? So, it is very easy to once you get the picture. So, first thing you have to understand is convolution correlation operations are very common and very useful, and you need an efficient way of computing them, and efficient way of doing this is by circular convolution correlation, because that exploits the fast Fourier transform algorithm available for computing the DFT. Okay. I think we will close the discuss. There are many more things. In fact, as I told you, it's could be both interesting and also boring, because boring in the sense that you have to keep appears to be keeping track of so many things, but no, it is only all those discussions and illustrations are only to clarify understanding, but you go in the wrong way. So, you think that, oh, there is so much to remember kind of. In fact, nothing to, if I have to remember everything, I would not be able to even talk to you. See? So, you have to logically flow from one to the other, it will be very easy. Okay, let us move on to, this is the this is about DFT, and why do we need DFT in speech technology? Because that is all what we are doing in most of our calculations. And next we will move on to a very important topic, which is for which all the background that we built will be useful, and unfortunately time. So, how much we can spend? So far, now I am, whenever I say system, it is discrete time system, that we discussed number of times, because we are. So, we said unit sample response. Now, you can, for the next few classes, probably you can forget about delta function, delta t will not come back again, except for the examination. So, what we are going back to the unit sample sequence, and the response of a system for unit sample sequence. So, unit sample response of a system, that is my Hn, and I said I can represent a system completely by Hn or alternatively if Hn happens to be a signal, I can see that I can visualize that as the signal is generated by an unknown system excited by the unit sample sequence, whichever way you want to look at it. So, Hn is a signal and system equivalence we already discussed. So, Hn is a representation of a system, okay, and this is what is generated, that is, when I say generated, you are assuming that some impulse unit sample sequence excitation of a system is what you are observing. If you are observing the system, you do not have to do anything. Okay. So, this is what most of the time we may have, let us say, and that is the signal also you may want to look at it. So, a system represented by unit sample response of the system, you get the point. And we also noticed that we could represent a system by H omega. And what is H omega? H omega is Hn e to the power of j omega n, you remember that, you see. So, H omega is another way of representing the entire information that is available in Hn, and hence it is a representation of this. This will help you to look at some features of the system, study. This will help you to study features of the system. What do you mean by study the features of the system? By sometimes by looking at this Hn, I cannot see certain things which I can see through this. I gave some number of examples earlier. Imagine my Hn is something like a sum of sinusoids or something like that, just for the sake of argument. Then you can see that you can't see from that some individual sinusoids, whereas the moment you put it H omega, you begin to see that. Of course, you will ask, why do you worry about sinusoid? Where is the sinusoid? You do not have to see sinusoid, but then I will tell you, we need something equivalent of that. Very soon we will discuss that in today's class. So, first I want you to understand that this it is exactly same as these are invertible. So, if you give this, at least you can write on paper the corresponding this and vice versa, and but they are in different domain, indicating that certain features which you cannot see directly here, you may see. See, that is the, and then there is at another representation of the system, which is called, which we are going to discuss now, is called the Z transform representation of the system, or it is also called the system function. This is called the frequency response of the system, and this is called the unit sample response of the system. So, system function representation of the system will help you to design a system. I will tell you what we mean by that presently. That is the next topic we are going to consider. So, and you notice from this you can get this if you want to, from this you can get this, or from this you can get this, all this is part, that is why the title equivalent representations. So, we will see the system function representation of a signal or a system. Notice both are equivalent, we have already discussed that. So, the HZ, that will help you to design a system to if you want to. In fact, then you have what is called a linear, I will write the expression for that, linear difference equation representation of a system. Linear difference equation representation of a system, and which is given by, we are going to discuss this in quite some detail. I will explain this later. So, you have Hn, Hw, H omega, Hz, and then Yn, Yn Xn relation. That way, actually the representation is, the unknowns are these. The set of m plus n numbers that you have, those are the unknowns, those are the representation of the system. And what is just as this is used to synthesize signals with desired characteristics. Desired characteristics. Notice this is useful for designing this. Once you design a signal, in fact you will notice that Hg, if you are designing it, Hg itself will have A case, B case. So using those A case and B case, you can see, you can generate, you can synthesize the signal with the characteristics which you have, with which you have designed this. So this is the, and what are these equivalent? In fact, this is what you need. Let us say if you want to synthesize somebody's speech or somebody's voice. You see, I know in one of the lab experiments you have analyzed your somebody's voice or your voice and found out these are the resonances for vowel R, E or whatever it is and so on. Using those resonances, I want to reproduce that using those numbers. If you just give those numbers, I can't say whose voice is it. But if you reproduce and play it back, oh, you can say this is this fellow's. You follow what I say? So that this enables. Get the point? And all of them are very simple to, of course, you can always, even a simple thing you can look at it as a very complicated thing and vice versa. So it depends on how you want to look at it, but these are all, if you understand the links, they are very, very simple. But before that, these two we have already looked at it, but with a little caution. We didn't, so far we are simply, we have written, for example, I said Hn, I never even said what this Hn means. That means I said minus infinity to plus infinity. And of course, I also said H omega. I said, all right, you take Hn e to the power of minus j omega n. You will get H omega, that is what I said. Who will give you that summation? What do you mean by summing with respect to this one and so on? You follow what I say? So you have to address this problem now. Until now it is nice to write it on a board or imagine this. Now you have to come to the practical things. What do you do? How do you? And obviously you will not have this. You may have infinite Hn, but in fact you will see there are many practical systems where you have infinite Hn. Still you can get this, but not by direct summation like this, but by some other means. We will see how to get that by some other means. You follow what I? And in order to do that, let us look at this next representation, this Hn representation of signals first. Z, and this is called the Z transform representation of signals. Hn is a signal. So the Z, of course, obviously, as all of you know, books out there written on, in fact library has at least about 20-30 books on with the title Z transform. So obviously you can't go and study all of that, although once you know this, it is very simple. In fact, of course maybe with some experience and having seen it lot of times, but that whole 500,000 pages book should be reduced to some 50 pages. That's all that is there, nothing else. Well, by making it 1000 pages, you have made it complicated. You see? So let us see what is the significance of this. Very easy, but before this you could see, all of you have studied or at least heard what is called polynomial. Example? Example? Huh? Quadratic. Yeah, I mean, that is what strikes us anyway. Okay? X squared plus bx plus c, you can't forget that. Okay, and that is called a quadratic or second order polynomial. Why? Because there is 2, highest power is 2. So in general I can write any nth order polynomial. Why? A1 x to the power, an x to the power of n plus an minus 1 x to the power of n minus 1 and so on, I can write like that. Where a1, a2, a3, an, all the things are important, the x is only a variable of the polynomial. Just as in a quadratic, x is only a variable of that quadratic. X has no role to play other than represent. Otherwise, if a, b, c are enough for me to represent the quadratic, I don't need that x. Okay, you get the point? So in a similar fashion, that means all my focus is on the a, b, c. Likewise, here in a signal, my focus is on this x1, x2, x3 or x0, x1, x2, x3, my signal. So, suppose I take this x0, xn, xn as a coefficients of a polynomial, and that is what I am going to do. I write this as xn as a coefficients of a polynomial and sum this over all n, let us say for the time being from minus infinity plus infinity. And you may say suddenly, of course, you will ask lot of questions. Notation, there is a g is my polynomial variable, and why this minus, there is no need. In fact, many books also talk about plus n, but it is just convention. You will see this convention has come from our electrical domain or computer domain, because z minus 1 is a notation for unit delay in digital systems. That is how it has come. So we will stick to that. Otherwise, there is no, if you are still uncomfortable with this, write y is equal to z minus 1 and make it as y power y n. I have no problem. All the results will be valid, no problem. So it's a, so I am perfectly, it's perfectly valid, but writing a polynomial in a variable called z minus 1. My variable is z minus 1 rather than z. That's all that. So if you define like this is called the z transform of x. Okay. That means, what do you mean by that? What do you mean by that is, if by chance, because this is the definition, if by chance I am able to get a compact representation, you may not get. If I am able to get a compact representation for Hz, even though it is an infinite summation, that means, you see, this is always an invertible thing, although we do not talk about in this course at least, the so called inverse Z transform. It is very easy, but again, that is what you, if you have studied in college Z transform, Laplace transforms, you would have done all of this, but anyway, we will very simple also, but so assume for the time being that given xn, if you can compute, get xg, given xg, you can always get xn. But why then, why go roundabout? Why can't I live with this xn? I told you already there is a purpose for this, plus apart from that there may be a compactness here, you see. And one simple example of that compactness is the following. My xn is the following. Up to infinity. That is my xn. That is x0 is a xn for n less than 0 will be 0, and xn greater than n will be this one. That is a power 0 plus a power 1 and so on. This is my xn values. Okay. And if I have this, of course, do I keep track of all these infinite numbers? No, not necessary. If only you find the xn here, xg here, you notice that it is simply 1 by. That's all. So simple. So this has all the infinite values that you want. You see? All of you know it is a polynomial expansion. If you write 1 minus a g minus 1 to the power of n, where it is of course n is infinity, then you know that this is simply 1 plus a g minus 1 plus a squared g minus 2 plus etc. This is what you will get for n. You see, I should have written like this, sorry. If you all of you have done this any number of times, don't tell me that you have not done this. Okay. So what do you find there? You can see I have a polynomial in z minus 1 with the coefficients as 1 a squared and so on. Of course, in this case it is possible. Right here. So that is one other advantage that we get in terms of z transform. Which one? Of course. You are right. You are right. In fact, that is where the z transform 1000 pages are there. Otherwise, it won't want me. But yeah, I agree. The convergence is that's why. In fact, I did mention this earlier a few minutes before. I said I can write if there is a possible to have a compact representation. I didn't say you can always have. You get the point? And that refers to convergence and so on. Of course, it is an excellent topic. We should all learn that, but unfortunately, that goes into the theory of z transform. And when we are computing in the computing domain, you do not have any problem. Always you are considering block of data. So convergence issue does not even arise. You get the point I am saying? But all the same, it is good to learn that, know that, because that helps you in designing. visualizing several things, but there is nothing I can do. It's not a course on that. Okay. And almost all of this Z transform is closely linked to, of course, what is called the complex variable theory, which all of you have studied and forgotten very well. I know it's just but it is so important. If you are at any disadvantage of learning anything, any subject, doesn't matter, even computer science, it's because you don't understand complex variable theory. And the moment you understand it, I will show you some examples of this, and everything looks so simple. It's just but unfortunately we skipped that, because complex variable theory is made more complex by the teacher, and of course you really want to make it complex by ignoring it by the students. That's how it had happened. Otherwise, so nice. Cauchy-Riemann conditions, Cauchy's integral theorem, Cauchy's residue theorem, all these are very, very nice, simple concepts, and absolutely essential. Okay? And all I am trying to reproduce now is what I learnt about 45 years ago. Okay? And if fortunately for us, teacher was good, and of course maybe we were also good, I don't know. In the sense that we didn't ignore. That's what I mean, not that you are bad, but we didn't ignore, or we could not ignore because they were asking the exams. And but you know, those ideas are simply fixed in our mind. There is no question of getting them. Forgetting doesn't arise. Okay. And that is a very crucial part of anything. You know, any engineering, including computer science is no exception. Because the moment you need to deal with the data from real sites, you will have to worry about this. But anyway, I have to skip some more, but you don't need this. If I need a representation like this, this is just a definition. First let us, don't worry, I agree, that is where all the convergence issues will not even discuss that, but we need only a partial set of results here. So, if this is the Z transform by definition of this, I would like to know what is, this is also written as what is called the Z of X. I don't know, I am using this notation, but probably somebody, I can't write all kinds of fonts here. So you better, this is an operation on Xn, notation. Z transform of Xn, read it like that, it is denoted as this, and that is the definition of this. If that is the case, what is the Z transform of Xn and minus 1? This is what I need to know. What is the Z transform of Xn minus? It's very easy. Start with the definition first. N is equal to minus infinity plus infinity, Xn minus 1, Z to the power of minus of, Z to the power of minus n. That is what you are writing. Notice, you follow what I just reproduced this Xn minus 1 in place of this what you will get. Now, you write the following. So, this exact Gn, you write it as n minus 1 plus 1, this is what you will get. Okay? So, now you can see this is Z minus 1 summation n x n minus 1 Z. Now, you replace this variable n minus 1 as m. So, you will get xm Z to the power of minus m. Got your point? Replace this variable as m. So, m. So, xm Z to the power of minus m summed over all m. When n is minus infinity plus infinity, m also goes from minus infinity, no problem. So, that means this is same as, and those of you who have studied digital system, you notice that you would have come across this. You see, all this simply means is that xn minus 1 is what? Xn minus 1 is, it is xn delayed by one sample, it comes one sample later. That is the meaning of that, isn't it? Xn minus 1 is a delayed one. So, delay is equivalent to a Z minus 1 operation. In fact, all digital systems use this delay as Z minus 1. So, several blocks of Z minus 1 means that many units of delay in shift registers, everything that you consider, this is what you do. So, unit delay, clock cycle delay if you want to call it. Okay? So, that is what it is. And now it is very easy. If it is x minus k, it will be z minus k. Okay? So, this is one other property we need. I think that Using these simple there are many more, I am not worried going to discuss that. And notice I did not say anything about it, z itself. That means I get a function, it is a polynomial variable. That means I get xz as a just as an illustration 1 minus a z minus 1. So, it is a function of z. What do you mean by function of z? Notice that z could be real, and in this case z could also be complex. Why can't you make it z? That means complex means two quantities at a time. Really, you can you don't have to write x plus ij. You can also write x minus comma y. As long as you can define the operations on that, it doesn't really matter. You don't have to necessarily insert that complex variable that j. Notice for the same reason, in principle, this z can be real, that means only one real number, or it could be 2, it could be 3, 4, anything n-tuple it could be. Then why is it that people are not using it? Because you don't have good definition of the operations on that. You have understood the operations up to 2 using a complex addition, multiplication and so on, but beyond that I do not have a good definition of this. That is what limited the exploration of that, otherwise it is. And another way of looking at it is, I want to compute this, you will see presently, I want to compute this for all values of z. If I take z only as a real, this one, let us take this again your quadratic ax squared plus bx plus c, that is my fx, let us say. I can compute fx for all values of real values of x. You notice that you are in trouble already. Why? Because if you are trying to find what are called the roots of this or something, or for what values of x, let us say that function will be 0, it need not be 0 for, let us say if my fx quadratic I am talking about ax squared plus bx and as a function of x, okay, and you notice that my fx is like this. If my fx is like this, notice that this is 0, you know, y axis 0 here. So, it is never crossing the axis, it is never crossing my axis. What do you mean never crossing the axis? It is never, that axis is your creation. It is never crossing the real axis, that is all. You see. So, what is interesting here is, in fact, you have done all of this, but still you are forced, your teacher asked you, okay, fx is make it 0. Then what did you come up with? You came up with x, a complex number. You came up with, there are complex roots for a quadratic, although my ABC are real, but you came up with the complex roots. How do you represent a complex root then? So, that means now you have to take a point not on the real axis, but on a 2-dimensional. You get the point I am saying? So, at those points the quadratic function is 0. That means you now take a 2-dimensional instead of a real axis now. In a real axis plot like this, it will, in a complex this one, yes, that function, this is a 3-dimensional plot now, because the points are on the 2 dimension and this is a 3rd dimension, and now you can see it crosses through the, a function will have a 0. You might have, you know, all this you should have studied, or you have studied, you might have forgotten, or you know, you thought good riddance kind of a thing, you know, that but you know, it's a, and the same logic. All I am trying to say is, although we are not discussing, no books discuss, because you do not know the operations on it. From 1 dimension you went to 2 dimension. That means you want to represent a point in 2D by a variable. As a variable, if it is real, it is on an axis. If it is a complex, it is on a 2 dimension. Why should I? Why can't we point in a 3-dimension space? And the function is a function of 3 variables. It's very common, isn't it? But I don't represent it anymore. But it is physically it is possible. A function can be represented as a function of 3 variables. And unfortunately, those 3 variables, the function of those 3 variables won't be 0 on a real axis of any of this. So, you need to worry about the 3-dimensional space, and that is a very common engineering problem. Why 3? 4 variable, why 4? function of hundreds of variables. But the point why you are not considering here, or a polynomial in more than real or complex two variables, two dimensional problem, is because operations are not defined, and also of course teachers, first of all they have to struggle, and then students have to struggle more to communicate that to the students. That is where the problems come. Otherwise, engineering wise, there are any number of engineering problems which require that. Okay. And you will see now, if you didn't have this, first of all in quadratic itself you are stuck. In a quadratic itself you are stuck if you didn't bring in the concept of a complex number or a point. When I say complex number, it is a point in a two dimensional space. You get the point I am saying? Anyway, so that is the significance of this. So G can be real or complex. In fact, it is complex. If it is real, one of them will be zero. The imaginary part will be zero. You understand, Alan? So this is a little more generality it will give. Notice that my coefficients are still real. But there are situations where coefficients are also complex. Then it's another problem, another dimension. But let's not worry about it. We are already into deep trouble here. So let us take the coefficients are all real. My signal is real. See? And now I want to represent this in this fashion. I am much more comfortable if I have a complex variable in the polynomial as a polynomial variable, and so that I have lot more flexibility. What flexibility we will see presently. All of you get this? I deliberate, of course I am avoiding a lot more details for the simple reason that it will divert our attention, although it is important to note this, but how far we can go. So now that is the definition of Z transform, and in fact I will combine these two, so I will not discuss much on this. First let us go to this. What is this linear difference equation representation of a system? And this is very simple. Any linear system, I said if xn is the input, yn is my output. That is what we said. Okay? And earlier all along we were saying that okay, if there is a hn is the unit sample response of a system, then of course yn is simply convolution of this, if from minus infinity plus infinity, all that we said. But now hn, you can't say that okay, give me those infinite sequence and represent this, you can't do that. So, but notice that all physical systems without exception, including speech production mechanism, has hn infinity. That means once you excite it, the sound never dies down. In fact, all the lectures I have given in this room are on the first day, they are still there in this room. If you don't want to listen, what can I do? There is nothing I can do. And what I gave last year and year before also, they are all there in this. It never dies down. Only thing is, its value goes down so much because it decays, so other things overtake, that is what. So that is why you are not able to see. So otherwise it is infinite. So obviously you need a more compact representation. So one way of looking at it is, and also let us say another way, let me forget about the fact that it is compact. Suppose I am able to represent this hn by a small number of coefficients. I have already illustrated one such by 1 by 1 minus a z power minus 1. That means if my system is represented by, in such a case, only by one number, that is a. If you give me a, I can produce the infinite unit sample sequence of that. So that is what it means. So if I am able to represent them, let us say by a sets of numbers called AKs and BKs, then the output, notice this can be represented, because it is a discrete time, output can be represented as a linear difference equation. A linear difference equation with constant coefficients, and that is what it is. Maybe I do not have to rewrite this, I can just. So you can see yn is my output. It is very simple to follow. No great thing. You see, you have to give a meaning to this. That's all. all that I am now writing this as, notice it is a linear system, there is nothing you can, so yeah. I am assuming all real, that linear constant complex can be assumed, no question, but you know, it makes the discussion more complex, that is all. Otherwise, yes, there is no bar on that. Signal also can be assumed to be complex. Can anybody see what is a complex signal? There are many ways of defining it. Of course, complex signal by itself has a meaning in mathematics and also in a, but I do not want to go into that, since you are not aware of it. Analytic signal is a complex signal, but I do not want to go into that. If you have studied complex variable theory, you would have understood that. But leave that apart, forget about, assume that you do not have any background of signal processing or any complex variable theory. What is meant by complex signal, or where is the need for considering a complex signal? Very easy, just stretch your imagination a little bit, you will get it. Huh? Excellent. That's the, see, it's not two output, but any pair of signals, you want to consider them together for some reason. That's the point. You see, you want to consider them together. I just happen to observe, let us say, some some variable and some other value simultaneously at time instant t is equal to 0, I observe two numbers. T is equal to 1 or 2 numbers like this. So, every time I need to consider pair of numbers. So, the best way, since I know how to, I can't ignore them, all operations are together, they go, but by themselves they may not have any link, but they may be related is a different, but I need to consider them together. So, such a thing can be represented as a sequence of complex numbers. So, that becomes a complex signal. And why only 2? Why not 3? Why not 4? That means 3 numbers at a time, 4 numbers at a time. It is not unusual. We are doing it all the time. In fact, MATLAB gives you can consider n numbers at a time in a matrix form. It does not call it, because complex you only use it for 2. So, you do not call it, but you can do some. In fact, that is why if you define a matrix with each column as another different signal, write FFT, it will simply compute the column wise FFT for each column separately and gives you the result of in again that many columns. MATLAB, you know what is it? All of you know what is MATLAB. MATLAB is matrix manipulation. You see, MA abbreviation is for matrix there, MAT, MATLAB. You see, so simultaneously you can, so there is no all the, if you, since it is not 2, you do not want to call it complex, but that is much more complex than complex. Complex is only 2. Yes, you have a question. No, I think no, you are wrong. First, let me correct you on this. It has nothing to do, the real of dictionary meaning of real and complex of dictionary meaning of complex is not there. Complex does not mean it is complex in the dictionary sense. Complex means you are trying to consider 2 at a time. That is all the meaning of complex. It is not the, and real means not the real world. Real axis means it is only one axis, that is all. It has nothing to do with the real of the real world. You see? No, then you are in trouble already. I can tell you why. Because I have x axis, y axis. I call, so all the numbers you consider y axis are imaginary, but they are also real numbers only. You see, they are not complex numbers anymore. It is just you happen to consider this pair of numbers together at a given point of time. So, do not mix up with this terminology. The mathematical terminology is very different from the dictionary meaning of it. Okay? Otherwise, we get into a lot of problems. So, this so what is this is important to understand very this is a, because it is a linear system, you can show that that system also can be represented as once I get my output for any input, I have got the system. That is what it is. So, you can write this output as a linear weighted sum of the past output samples. Y n minus 1 is the previous output sample, y n minus 2 is the previous to previous output sample. So, y n minus k will be the kth previous output sample. So, you have y n current output will be a already collected the previous outputs. So, it is a weighted sum, that means you weight the previous one by a 1 y n minus 1, a 2 y n minus 2 and so on. So, if you can represent it by y n as a linear weighted sum of the past m samples plus a linear weighted sum of the past and the present input sample. There is a present because k is equal to 0. If k is equal to 0, it is b0 x0 xn. b0 xn is my current input sample, xn minus 1 is the previous input sample. So, if I am able to represent the output by a linear weighted sum of the past and the present input sample, then it is called the linear difference equation representation of a system. And in fact, you have studied this. You have studied this much more sophisticated and complicated thing than this. This is a simpler version of this. Where did you study? You have studied it right from your 8th standard. The so called linear differential equations are exactly this. The linear differential equations of first order, second order, third order, if you see with some constant coefficients, is exactly this. And any differential equation represents a physical system. I do not know whether you know that or not, but anyway. Okay. And so, this, but since you are considering the discrete time system and a discrete time signal, so this became differential equation became a difference equation. Difference equation is a lot easier to visualize, solve and so on than difference equations, differential equations. You get the point? Anyway, let us not go into. So, that is what it is. That is why it is linear difference equation representation of a system. So, you can see now given any xn, I can always get my yn provided I know these a case and b case. If I know a case and b case, give me any xn, I can get my yn. That means a case and b case represent the system completely. And this is the one that we are going to use in speech, as you will see presently. Okay. So, now let us see. So, this is, you may say, what is this minus? There is no sanctity about minus. We can always absorb it in this. Now, before we do that, let us do the following: yn plus ak y n minus k, k is equal to 1 to m is equal to summation bk x n minus k, k is equal to 0 to, and of course, you can also write this as 0 with a0 as 1. You see, so both are same. You got the point? So, I can write this in this fashion. That is the reason why I put minus here. You understand what I say? A0 into y1, yn. Okay? A0 is 1. That is how you observe yn here. Now, what you do, I am not going to do all of this, you should do it as an exercise, very simple to do. Take a Z transform on both sides. What do you mean by Z transform on both sides? Multiply both sides with z to the power of minus n and sum it with n. Notice that this does not have a summation with n, n is constant. So, you can multiply both sides with z to the power of n and sum it with n. Okay? And I think some simplification you can do that. I have already shown. Now, you bring this, interchange the summation, put this there and so on. I am going to write the final result here. Where a0 is 1, because you do not have to make a0 can always be made 1. Why? Even if it is non-zero, just divide everything both sides by all coefficients by a0. Okay? You will make it a0. So, no loss of generality here. So, Anyway, you better figure out how to do it. It's very, very simple to do. So, this is what you will get. And now you can see, I can write as follows: yz by xz is equal to summation bk z minus k is equal to 0 to n divided by k is equal to 0 to n m bk. And this is, you see, notice what is it yg? Yg is the z transform of the output sequence, xg is the g transform of the input sequence. So, the ratio of these two g transforms, you give a name for that, and it is called the system function. It is called the system function. It is called the system function. The ratio of the g transform of the output by the g transform of the input is called the system function. And notice that the system function is completely determined by these coefficients a case and b case. You get the point? Why? Because give me a case and b case, m plus n numbers, m plus n plus 1 numbers. But even b0 is not required because it is called a gain factor, but does not matter. Let us not worry about those details. I will. So, if given this a case and b case, you can get the system function completely. And what is the advantage? That means, so notice this is provided if it is possible. Notice there is a if clause here. I have infinite response here, but if I can represent it by a finite set of numbers like this, then you can notice that the system function can be represented like this, and then you can do lot of things. One interesting thing here is, you can see from this, you can find out what is called the unit sample sequence for this, of this system. First of all, you can generate Hn even though it is infinity from these finite numbers. Can anybody see how? From this finite set of numbers, I can generate Hn which could be infinity. So, how do you do that? From this. That is why this is important. I wrote below and erased it. This is used to generate and synthesize the signal. So, now what happens is, make Xn a delta n, Xn a delta n, and keep collecting this y. Since Xn is delta n, you make initial condition y minus 1 minus 2 0, because they, and because that is the previous output. Since you are not even applied the input, so you can make all the initial conditions 0, and so Xn is equal to delta n, and then the resulting yn will be Hn. And notice that Hn will always be infinity, even if there is even one non-zero value here other than a0. If other than a0, if one non-zero value is there, Hn will always be infinity. You see? So, I can generate an infinite value by this. All of you get this point? Is it, are you finding it difficult? It is very easy, just you have to write these equations a few steps, that is all. Instead of m and n, make it 1 or 2 or something, then it will be easier. Then you write Xn is equal to, Xn is my input, Xn delta n, then you write that, just write 1 or 2 steps, it will be easy to follow. So, you will get yn is equal to Hn. Even though Hn could be infinite, as I told you, even if one of the AKs are non-zero, because each output will be dependent on the previous output. So, you keep circling like this, even though there is no input. The input could be 0, delta n is equal to 0, non-zero only when n is equal to 0, for all others it is 0. So, this vanishes very quickly. So, only this yn depends on the previous output, so you generate infinite amount. That is how you generate Hz. You get the point? So, this Hz is a much more general representation, provided of course, and from that you can get all Hn. And you can also get H omega. You can also get H omega from Hn. How do you get H omega from Hn? Very simple. You have done all of this. You have to just recall what we have done. If you recall, what is my H omega? You remember that? That is my H omega. Okay? Ask me if you have any doubt on this. It's a, so if my z is equal to e to the power of j omega, If my z is equal to e to the power of j omega, am I not, all of you are clear? This you know, I have not introduced anything new here. So, if my z, if I write e to the power of j omega as z, it is exactly same as this. Conversely, if I substitute in hz, z is equal to e to the power of j omega, I will get my h omega. So, that is what you have to do. You substitute, h omega will be all of you understanding what I am saying? H omega is simply obtained by substituting this. Now you see, this is a very, very interesting point, which, because since you did not study complex variable theory, or even if you study forgotten, you are a little lucky, because otherwise in those days they did not know what was happening. And I will tell you one interesting thing with here. First, let us look at this Hg. This Hg, what is G? G is a point in a two-dimensional plane. G is a point in a two-dimensional plane. So, what is Hg? Hg is like some value at each point on the two-dimensional plane. Hg is a value of this function at each point. All of you get it? And this space is infinity. After all, G in the two-dimensional space from minus infinity to plus infinity on both the axes. So, I can take any point in this infinite two-dimensional space, I will get correspondingly for each point a corresponding value of Hg. Because Hg itself is complex, that is a different matter. So, I need two infinite two-dimensional planes. On one I put the real part, another part imaginary part of the Hg. But let us assume for the time being one of them, let us say, or magnitude or whatever it is. So, notice that given this functional form, no matter what these AKs, BKs and so on, given this form, I can compute in principle my Hg for all values of z. It is almost like, okay, having like a shamiana or a tent kind of a thing. Just imagine a shamiana like what Jayalalitha built for this wedding, huge wedding, a huge one you need. So, imagine an infinite shamiana like that, you see. You get the point? So, that is for every value you have some height of that shamiana. That is my Hg. Got it? Now, so that means Hg is a very general function really. And what you are doing here is, you can see this is my z plane, where real part and imaginary part, and this is my z plane. So, in this z plane, as I told you, for every point I have a value. So, this is my ground, and I have this shamiana type of a thing, you see. So, now what is the g is equal to e to the power of j omega? G is e to the power of j omega is simply, you see, this is my omega, and this point is, what is this length of this? 1, because r is 1, and omega is simply a angle. And you notice g to the power of j omega, it is always omega is periodic with 2 pi. For every 2 pi, it comes back to the same point. So, my omega goes from 0 to 2 pi. Okay. So, so the e to the power of j omega, omega from 0 to 2 pi covers that circle called the unit circle. So, you have a unit circle, and what you are asking here is, what are the values of Hg on this unit circle? It is almost like saying, suppose you had some reference origin somewhere, and somewhere you ask somebody to bring a unit cylinder, with a unit radius, and you simply insert that cylinder there in the middle of the shamiana, that is all. So, what happens is, wherever the cylinder cuts that shamiana, those are the values you are talking about here. You follow what I am saying? So, that means you are not talking about all values of this height of Hg, but only a small subset of them which is on h e to the power j omega on this unit circle. You get the point? So, now you can see this is much more general. Sometimes this may not even exist, but this always exists, you will see. Anyway, basically what I mean is sometimes you can't sum this, and one simple case that you can't sum is if Hn is 1, let us say, or Hn is some sinusoid signal or something, you can't sum them. But this Hg exists. What do you mean by Hg existing? Hg existing means what happens here is, it is likely that I will come to that. First let us get okay, I will just take 2 minutes on this and then we'll go into the details of that, but let us look at this existing non-existing part of it. I want to explain that. Notice that for some values of g, since g is complex, just as quadratic also is 0 for complex values of x. So, likewise this polynomial also will be 0 for some values of z. So, whenever that is 0, what happens to Hz? Infinity. Hz will be infinity at those locations where this polynomial is 0. And how many such locations are likely to be there? If it is an mth order polynomial, there will be m roots. There will be m roots, real or complex. When you say real, they are on real axis, otherwise it is anywhere in the g plane. So, there are m roots. That means at m locations in this 2-dimensional plane, the value of Hg is infinity. Get the point? Yes, I agree. That is a cancellation of this, but let us assume for the time being that does not exist. It is, once it is, both are equal, what you are saying is both are equal, anyway it cancels out. No, wait, you are not following my point. All I am trying to say here is, suppose there is a term here, after all each polynomial I can express it as equivalent of first order polynomial, let us say. So, what you are saying is there is a first order polynomial, both are equal. If they are equal, I will cancel them, I do not need to consider them. So, the 0 and pole gets out of it. So, the order will be reduced. You see what I am saying? So, you consider only those distinct ones which do not cancel, because if they can, if numerator also, after all that way I can add always some more, one more polynomial, same polynomial as the denominator. That does not make any sense. So, you can as well cancel that. So, that is not a problem. So, the interesting thing here is, what did they say? There are at m locations points in this z plane, they can be anywhere, at which Hg is infinity. Okay? And now take this one. The roots, at each of these roots, what happens now? Hg will be 0. So, that means at n locations, m locations it is infinity, at n different locations it is 0. And the most surprising thing here is, I do not even need to know the height of the Shamiana. All I need to know is, tell me those points where it gets infinity and where it gets 0. Give me that m plus n locations on the g plane, forget about what Shamiana somebody has used. I can reconstruct the entire Shamiana by giving these things. You follow what I am saying? Basically it is almost like, of course, very crude analogy which I always give in this class to fix the ideas is like this. Of course, imagine still a Shamiana, but it is not required, but you can see our Shamiana building or tent building is a much better example, even Shamiana also. How do you build a tent? You put some poles so that the cloth stays there, and if you just only put poles, what happens? The cloth will not, it will not stay. What do you do next? You also pull it and peg it. So, at each point of the moment where you put a peg there, you are stretching it there, and the moment where you put a pole there, that is going up there. So, the location, and suppose you have built something and somebody pulls somewhere else and pegs it, not the shape, whole shape will change because of this. Whole shape will change depending on, and somebody comes, puts a pole, of course, as long as it doesn't pierce and break the cloth, but otherwise it will create another hill and changes the shape of everything. So, what it basically means is the locations of these roots which correspond to what is called the infinity of this, and the locations, the numerator polynomial where it is 0, 0 corresponds to pegs location, and this infinity locations correspond to the poles location, and that is why it is also called a pole. The zeros of this is called a 0. So, pole and 0 location in the Z domain if we give, I can reconstruct the entire tent. That is the sheer beauty of this one. So, and once you can construct the entire tent, I can also get a subset of this, that is this one. Just put this in. Get the point? So, that is the story about this. It's a simple thing, but it's good to have a see, in fact, this is one thing which even 30-40, it always bothered us in complex variable theory when we studied. What is all these poles and zeros, entire function, and it never got fixed in our mind for a long time. It's very obvious. I simply don't need the Shamian anymore, height of the Shamian anymore. Keep telling me where you are going to put the pegs and poles, that's all. Once you give me the locations of the pegs and poles, I can tell you what will be the height of this. That means Hz for the entire Z plane is determined by the locations of these roots of both numerator and denominator polynomial. And once you have that, this unit cylinder you put at the origin, you can also cut the. So, notice that again the important point here is the moment you add one more root somewhere, either in the numerator, that means it is not affecting only at that location, but it is affecting the entire thing. In fact, you may say, why do I need this? Exactly what you do in speech synthesis, that is the point. It is not that poles and zeros are pegs and poles are Shamiana and tens and so on, but it is the speech synthesis also exactly same thing has happened. Where you locate decides what sound you are producing. That is the beauty of this. We will discuss that later. I think I need another hour. At least hour and a half. So, one more class we need, we will do it on Tuesday. Okay? We will stop at this point. Unfortunately, you don't get material on this anywhere. So, it is there of course, but not in this class. So, you have to follow what is going on in the class. Once you understand that, you will be able to follow the literature. Okay? We will stop.